A bit of physics. Specifically, we'll be solving problem 42 from chapter 16. And the problem is two equal charges are situated at the diagonal corners, A and B, of a square that has sides of 1 meter. What is the magnitude of the electric field at point D? So each one of these sides is 1 meter, and we know our charge is 1 nanocoulomb, and both of them are equal. So let's get started on our solution. Step 1, we have to calculate the electric field at D due to charge A. And the distance between D and A we know is 1 meter since they're perpendicular on the square. And according to Coulomb's law, the electric field is equal to the Coulomb's constant times the magnitude of the charge divided by the square of the distance. So the square of the distance in this case is just 1 because 1 squared is 1. And Coulomb's constant is approximately 8.99 times 10 to the ninth. And we have to multiply that by the magnitude of our charge, which is 1 times 10 to the negative ninth, or 1 nanocoulomb. And so the magnitude of the electric field of D due to A is approximately 9 nanocoulombs. And now to get the direction of said magnitude, since A is positioned exactly above D, or perpendicular to D, or above D it's above D, the electric field is actually going to point downwards. And more specifically, because the magnitude is positive, the direction of the electric field will point away from the charge. So our vector EAD is 9 nanocoulombs pointing downwards. So now we have to find the electric field at D due to charge B. We do the same process we did for A, which is get the distance, which is 1 meter, and then use Coulomb's law to find the electric field. And in this case, both charges are the same magnitude, and so we get the same calculation. EBD is also 9 nanocoulombs, but the direction is what will be different. Since D is positioned to the right of B, the electric field at D due to B will be along the left axis. And remember, since the charge or the magnitude of the electric field is positive, it points away from the charge. So it will be pointing to the left. So now we know EBD is 9 nanocoulombs to the left. And now for our final step, we have to find the resultant vector, or the resultant electric field, at D due to EAD and EBD. So we know EAD is 9 nanocoulombs downward, EBD is 9 nanocoulombs to the left. So if we notice here, these 3 points can make a right triangle since this is a square. Both this length is equal, this length is equal, and it makes a right triangle. So we can use the Pythagorean theorem to find the resultant magnitude. So the resultant magnitude is equal to the square root of EAD squared plus EBD squared, which is equivalent to around 12.7 nanocoulombs. Awesome, so now we have the magnitude. 12.7 nanocoulombs, Pythagorean theorem, now we have ED. Now, since both of these vectors have the same magnitude, we know the resultant direction is going to be 45 degrees. We can prove this, though, by doing the tangent of theta is equal to EAD over EBD, which is 9 over 9, or just 1. To solve for theta, we can do the arctangent of 1, and the arctangent of 1 is equal to 45 degrees. So just to recap on that, we know this is 90 degrees here, this is 90 degrees here, and the angle that bisects two 90-degree angles is 45 degrees, but mathematically, you have to use the tangent to get that bisecting angle. And so the bisecting angle of 9 over 9 is the equivalent of, or the tangent theta of 1, and then the arctangent of 1 is 45 degrees. And thus, the solution to this problem is the magnitude of the electric field at point D is equal to approximately 12.7 nanocoulombs at 45 degrees.